going to start by going through Dijkstra's, so graph algorithms, and then I think Ashpreet's going to take over for sorting algorithms in a bit. But starting with Dijkstra's, cool, that works. So before we do that, a path, this is a definition of a path. It's a sequence of vertices such that vi and vi plus 1 are connected by an edge for all I in between 1 and n plus 1, n minus 1. So it's just a bunch of nodes that are connected by edges, basically. A shortest path from A to B is a path for which the sum of all of those weights is as low as possible. So out of all of the paths between those two nodes, the sum of the weights are as low as possible. And the goal of Dijkstra's algorithm is to find that shortest path. Okay, let's say we have a graph like this. We're going to try and run Dijkstra's on this. So what would be the first step we do? Or in a sentence, can someone tell me how Dijkstra's works? So with A being our initial node, we want to explore the node with the smallest distance that hasn't yet been visited. Initially, we set the distance of our initial node to 0, because to get to our initial node from our initial node, we don't have to do anything. And we set the distance of all the other nodes to infinity, because we've not actually found a way of getting to them yet. And we also store the previous node, so the node that we came from to get to a node. Initially, we just set this to itself, because we don't know how to get there from anywhere else. And we set them all to not being visited. Yeah, this is being recorded. Okay, so we start A, not quite, so first we want to visit A. So first we look at A's neighbours. We say A, we can get to B with a cost of 3. 3 is less than infinity, so that improves this distance here. We can get to C with a cost of 5. 5 is less than infinity. So we can put that there, and we mark A as visited, because we visited all of A's neighbours. Then we look at the next smallest node with the smallest distance, so in this case it's B. To be fair, yeah, in a lot of algorithms you'd probably set the node to visited and then look at its neighbours. So say we set B to visited, then we look at B's neighbours. So from B, we can get to A with a cost of 6, because we can use 3 to get to B and then use 3 to get back to A. But 6 is not better than 3, so we'll ignore that. We can get to C with a cost of 5, because it's this 3 plus this 2. 5 is not less than 5, so we'll leave that how it is. It doesn't improve the solution. And from B we can get to D with a cost of 7 plus 3, so 10. 10 is less than infinity, so that improves our solution there. So we can set this to 10, and we can set this prev to B. One mistake I've made, I think you're about to point it out, but these two, we'd also update their prev values to A, because that's where we came from when we explored those two. Yeah. Cool, I saw Fred typing, I was like, yeah, what have I done wrong? Okay, so we visited B. Now we look at the next node with the smallest distance that we haven't visited yet, and that would be C. So, from C, we can go to A with a cost of 5 plus the 5 we used to get to C. We don't want to do that, because 10 is not less than 0. We can get to B with a cost of 5 plus 2, so 7. 7 isn't less than 3, so that doesn't improve that. And we can get to D with a cost of 25. 25 does not improve that. And finally, we can get to E with a cost of 5 plus 15. So with a cost of 20. 20 is less than infinity. So that's the best we've got to get to E right now. And we update this to our prev node, C, which is the one we just visited. Okay. So now we look at D. That's the lowest distance that's not visited yet. From D, we can get back to B with a cost of 17, because it would be the 7 plus the 10 we used to get to D. But we don't want that, because 17 is not more optimal than this 3. C, we can get to with a cost of 30, because it's 10 to get to D, plus 20 to then get to C from D. 30 doesn't improve the situation there. And finally, to get to E, it's 10 plus this 2, 12. 12 improves this here, so we can replace this 20 with a 12, and replace this prev with a D, which we mark as visited. And finally, we have one more node. So we just want to be exhaustive and visit this last node. Visiting E, 12 plus 2 doesn't improve, because 14 is not less than 10. And if we use 12 plus 15, I believe that's 27. 27 does not improve our route to C, so we ignore that as well. And we can mark E as visited. And this is when our algorithm is complete, when we visited all of the nodes. Yes, this last column is just full of ticks. And I believe that is what I also got. Yeah, cool. Okay, so this is the result of running Dijkstra's algorithm. Now say we want the shortest path from A to D, or A to E. How can we get that? E would, I'm not entirely sure, but I'd probably just stick to being exhaustive, because a lot of the pseudocode does just loop through every node until no unvisited nodes remain. Yeah. So how can we get the path from A to E? Look at the prev of E all the way back to A. Yeah, perfect. So we look at our destination. In this case, the prev of the destination is D. So E is our destination. To get to E, we come from D. To get to D, we come from B. To get to B, we come from A. A is our source. So we've reached our initial node. And so we found our path, our shortest path from A to E. From this table, can we get the shortest path from, say, B to D? Or from B to E? Will we be able to do that? No. Good. Yeah, so with Dijkstra, we always have one initial node. And we can get the shortest path from that initial node to any other node. But we can't get shortest paths between any of these nodes here. We can only get it from the initial node to some destination node. And it has to be connected to that initial node in some way. Okay. This is just the initialization of Dijkstra. So we set the shortest... So we set these three sort of arrays. We keep track of 3 different values for every node or for every vertex. We keep track of the distance from our initial node V to that node W so far. Initially all of these are infinity, except for the distance of our initial node, which we set to 0. We keep track of the previous node we came from, so the predecessor. Initially we just set this to itself as a convention. And we also keep track of whether we finished the computation of a node or not. So that was our visited column up here. We keep track of whether we visited or not. Okay, and initially we set them all to false. This is the actual pseudocode for the algorithm. So we set all of the distances to infinity, and then we set the distance of our initial node to 0. While there's unfinished vertices, so while anything in that last column has not got a tick in it, basically, while we've not finished every single node, we set W to the unfinished vertex with the smallest distance, so whichever one has the smallest distance at that point. And then we set finished of that node to true, and then we loop through every neighbor. And if the distance to that node plus the weight of, well, if the distance to W plus the weight of the edge from W to U, so imagine our distance to W is something like 20, and our weight from W to U, the weight is X. If 20 plus X is less than whatever distance we have stored for U already, say we have 30 stored here. If it's less than 30, then we switch the distance to U to 20 plus X. And we get rid of the previous sort of keeping track of where we came from. And we just say, okay, set the distance to this new distance and set the previous to where we came from. So we came from W in this case. And so this means we can keep track of the shortest distance. And that was the comparisons we were doing here when we said, for example, is 20 less than 10, is 3 less than 5, then we update it. We just have to compare those distances and see if it improves the distance and it's better than what we currently have stored. Does this pseudocode make sense to everyone? Are there any lines here anyone's sort of unsure about? Cool, let's move on. Complexity of Dijkstra's algorithm. So we can either use an adjacency matrix to represent the graph, where n is the number of vertices, or the number of nodes, and m is the total number of edges between those nodes. And we do the following up to n times. We mark every node as finished, we update all of the neighbours of W, and then we find W which is unfinished, and with the smallest distance. And the time complexity of doing this with an adjacency matrix is O of n squared at worst, because we're doing n operations, or something linear to n operations, up to n times. Obviously it can be better than that, but this is just our worst case complexity for Dijkstra with an adjacency matrix. With an adjacency list, so storing it like this instead of a table, having a list of nodes we can reach from one node, obviously this will probably be pairs of nodes and distances. It takes O of n to mark each node as finished, O of m to update every neighbour of W, and O of n squared to find which W is unfinished and has the smallest distance. O of m, I believe, is just the number of edges, whereas O of n is the number of nodes. And so this becomes O of n squared plus m, but because we just care about the headline, this plus m is negligible, so this is just O of n squared. And that's how we sort of get that time complexity there. We can speed up that third step of finding the unfinished node with the smallest distance by using a min priority queue. So I believe we're going to look into this in the session later on today. But with a min priority queue, we can keep popping off to the queue whichever node has the smallest distance. And it just means we don't have to check every single node every single time. And these are the complexities for if we do that. If we use a binary heap, we can improve the complexity to O of n log n plus m log n. And if we use a Fibonacci heap, we can improve the complexity to O of n log n plus m. Yeah, so this is the sort of calculation how we can derive those two time complexities. But that's just something to keep in mind. We can speed up that third step by using a priority queue. Okay, that's everything on Dijkstra's. Are there any questions about... Ooh, okay, wait. Are there any questions about Dijkstra? Okay, next part of today is minimum spanning trees. So, minimum spanning trees. A spanning tree is just... I should probably change this to say minimum spanning tree. Okay, a minimum spanning tree is a minimal possible selection of edges in a graph that connect all the vertices, but there's no cycles. So if we had this graph here, this pink highlighted connection of these nodes would be an example of a minimal spanning tree. If we had this edge connected, this wouldn't be a minimal spanning tree because it's cyclical. But this is a minimal spanning tree. And so there's a few algorithms we can use to work out these trees. Jarnik Prim is where we iteratively extend the tree with an edge which has the smallest weight and connects a yet unconnected node until no such edges remain. So, say we start with this graph here. What edge would we expand first? 2. Yeah, so we'd expand this 2 because that's the smallest edge out of the ones in the front here, you can imagine. And then we'd expand this 3 because that's the smallest edge. And then this 2 is the smallest edge. So we're only looking at the ones that directly connect an edge that isn't connected to an edge that is connected. So then it would be this 4. Then we connect this 5 because that's the smallest edge. This 6 is then smaller than this 7, this 10, and this 7, so we'd connect that 6. This 1 is the smallest. And then at this point we're done. If we connect any more edges together, we won't have it will be cyclical. So this is our final minimal spanning tree. And this assumes that the graph is entirely connected. There's no nodes out here, for example, that just aren't connected to anything. And that's how Jarnik Prim works. This is how we could implement it. So for every vertex of the graph, we keep track of the distance from the tree for every node. Initially, this is infinity. We keep track of the vertex which connects to the tree. So initially, this is just itself, quite similar to Dijkstra. And FW tells us if W has been added to this tree or not. And we set this to false as well initially. So this is our pseudocode. Set the distance of our initial node to 0, assuming we want to start at vertex 0. While there's unfinished vertices, so while there's false in this f, well, f of some node is false, we want to set w to the yet unfinished vertex with the smallest d of w, and set f of w to true. For every neighbor, u of w, if the weight from w to u is less than du, then we set du to that weight, and we set pu, which is the vertex which we came from, to w. So it's quite similar to Dijkstra in that way. Is this guaranteed to always find the minimum spanning tree? It is, as long as our graph is connected. Yeah. Okay. Time complexity of Jarnik Prim. If we have an adjacency matrix, O of n squared, because we have to look at every node and every vertice for that node. Adjacency lists. if we use a binary heap, we can get O of n plus m log n, where n is the number of vertices or nodes, and m is the number of edges. Fibonacci heaps, O of n log n plus m. I don't believe we need to know the derivation for these two, but again, something to keep in mind is we can get a better than O of n squared complexity by making use of these other data structures. Okay, one thing I want to go over now, before we go over Kruskals, is union find. So, what union find lets us do is it allows us to make sets. It allows us to find the representative value of a set, and it allows us to union two sets together. So, let's look at it in practice, and then we might understand the pseudocode a bit better. So initially, we might have all of these nodes start as their own sets, their own singular sets. So we make set for all of these nodes, and what that does is that essentially just points every node to itself. Every node is its own parent. And we can see what this arrow represents. It represents that PV equals V. Or it says V points to its parent. And everything's its own parent initially. Okay, if we want to union two things together, can anyone tell me what we do? Say we wanted to union this B and this D together. What would we do? So if we want to union these together, we'd set one of them to the parent of the other. So let's just use a convention where we set the parent as the closer to beginning letter of the alphabet. So let's set B as the parent of D. So D will now point to B. And this is a result of calling union with the two nodes B and D. This would be the same as calling union with D and B, because we just have our ordering convention where we point to the earlier letter in the alphabet. Both of these would have the same impact. Okay, let's say we want to merge F and D now. What could we do? We want to union F and D. Union B and F. Yeah, good. So what this find method does is it tells us what the top level parent is, or the representative value is for any node. So if we called find on D, this would look at D's parent, and it would look at B's parent. Because B's parent is equal to itself, it would just return B. That would be our base case. So find D equals B. And so find F is just going to equal F, because F is its own parent. And so what we do is then we merge those two parents. So we say, let's point F to B. And now, all three of these are in the same set. Even though these two don't have any relationship between one another, they both point to the same parent. Okay. So like union, find D, find F. Yeah, so that's essentially what, if we look in the pseudocode, we find A, we find B, and then we set the parent of B to... That's not right. I believe this should say A. We set the parent of B to A. Yeah. But yeah, that's essentially what we're doing. Okay, to check if F and D are in the same set, what do we do? If we want to see if F and D are in the same set, can it be the other way around? Yeah, I mean, it just depends on what convention you use. But, oh, right, are you saying if we did something like this? Yeah, that would actually work anyways. I don't think it would affect the overall behavior of it. Yeah. Okay, how can we check these two? Well, not quite double-ended. So in union find, everything always has a parent. So doing this wouldn't be right, because then we don't know which one's a representative value. So we always have to point to some representative value. If find F equals find D, good, yeah. So if we did find F equals find D, this would be true if their representative value is the same, and it would be false if one's representative value is something else. And so we can use this to see if two things are in the same set. Cool, okay. So that's how union find works. And we can make use of union find when we want to find minimum spanning forests. Cool, minimum spanning forest. So a forest is just a set of trees. So for example, if we had a set and we had this tree here and we had this tree here, this makes up a forest. And a minimum spanning forest is just a set of minimum spanning trees. Okay. Kruskal's algorithm lets us get a minimum spanning forest from a graph. And this graph doesn't have to be connected. So we could have something like Z, Y, X up here. And it would give us a set of trees. We'll assume that it is connected and it will just return us a set of one tree. But just keep in mind that Kruskal's can work for an unconnected graph. Okay. So how Kruskal's work is, I believe we... Okay, let's trace through it and then we'll look at the pseudocode. So with Kruskal's, we connect the smallest edge, which connects two nodes that aren't connected to each other. So initially, we're going to connect this E and this H, because this 1 is the smallest edge in the graph. Cool, yeah, so we connect this E and the H together. Then we look at the next smallest edge. So it can either be this 2 or this 2. How we implement which one we choose is up to you. I've just connected this 2 first. Then we can connect these 2 together. Okay, then we look for the next smallest. This 3 connects the C and the D. So we can connect that up. Then we've got this 4. Out of all of the edges, this 4 is the smallest edge. So we connect that 4 up. Then the 5 is the smallest edge. Then this 6 is the smallest edge. Then this 7 and this 7 are the smallest edges. But we don't want to connect them up because those nodes are connected already. So then we're going to have a cyclical tree, and we don't want that if we want a minimum spanning tree. So at this point, we're done. Our Kruskal's algorithm's completed its run through. And note that this returns a set of one tree. This isn't a tree. This is a set containing one tree. So it's, yeah. Cool. For example, if we got rid of... I'm just trying to think which ones I got rid of. If we got rid of... Okay. DGF. Yeah, so if we got rid of this and we got rid of yeah, that's where we get forest. If we have an unconnected graph like this and okay. If we had this graph here, this would lead us to a forest of minimum spanning trees. So these aren't quite minimum spanning trees yet because we've got a cyclical path here. And let's just make a cyclical path somewhere here. Okay. This isn't a minimum spanning forest yet. But if you returned one step earlier, we'd have two. Yeah, so if we returned at this step here, for example, we'd just have 2 spanning trees. One here and one here. Yeah, we remove the edges that weren't visited. So say we have these 2 here. This isn't minimum yet. So what we'd want to do first is we'd want to connect the edge that connects the smallest edge, which is this one here. And then this 2 is the smallest edge. And then this 3 is the smallest edge. Then it's this 4. Then it's this 5. This 7 is the smallest, but it connects 2 already connected nodes, so we wouldn't do that. This 12 is the next smallest. And at this point, we'd terminate. We'd say we've generated our 2 minimum spanning trees, and this would be a set of 2 minimum spanning trees. This would not be a single tree. So Kruskal's always returns a set of trees. Why did you remove DGF? Oh, I just did it to show an example of an unconnected graph. Just to show how Kruskal's would work if the graph wasn't all connected together. If it was 2 disjoint. Yeah. But yeah, that's how Kruskal's work. So it could return a set, or it could return... Well, it will only return a set. Whether that set has 1 element, 2 elements, as many as you can imagine. Kruskal's always returns a set. Okay. Complexity of Kruskal's. This algorithm requires sorting the graph edges by weight, which is O of E log E, if we use something like merge sort, where E is the number of edges. Then it does a linear search through the edges, during which it carries out only operations of O of 1, contributing O of E to the overall complexity. The reason why this is O of 1 is because the amortized complexity of union find, unioning two sets, is O of 1. And so the final complexity is O of E log E plus E, because it's this E log E plus E. E is at most n squared minus 1. So E is the number of edges, and at most n squared minus 1, where n is the number of nodes in the graph. And so E log E just translate to E log n squared, E log n squared minus n. Take the headline of that, it's just E log n squared, and E is n squared minus 1. Take the headline of that, n squared minus n, headline of that is just n squared. And this just turns into 2n squared log n. So our time complexity is 2n squared log n, which is just O of n squared log n, or O of E log n, however you want to write it. But yeah, so it depends on how dense your graph is or how sparse your graph is as well. Cool. Are there any questions about that?